From the moment humans first looked up at the night sky, we've been asking the big questions. What if life as we know it didn't actually start here on our blue planet? This is the captivating idea behind panspermia, a theory that suggests life's seeds were sown across the cosmos, eventually taking root on Earth. Could we be the descendants of extraterrestrial microbes carried across unimaginable distances to this very planet? Let's dive into the intriguing world of panspermia, exploring the evidence, the challenges, and the profound implications of this theory. Our journey takes us from the microscopic world of bacteria to the grand stage of cosmic events, all in pursuit of answering that fundamental question: where did life come from? The word panspermia itself holds a clue to its meaning. Derived from the Greek words pan, meaning all, and sperma, meaning seed, it literally translates to all seed. These seeds, in the context of panspermia, are thought to be microorganisms hardy enough to withstand the harsh conditions of space travel. Imagine tiny bacteria encased within rocks and ice, surviving the vacuum of space, shielded from deadly radiation. They journey for eons, dormant yet potent, carrying the blueprint of life to new and unknown worlds. Upon impact with a planet like Earth, these microbial voyagers could potentially awaken in the newly found hospitable environment. They would then begin to multiply and evolve, eventually giving rise to the rich biodiversity we see today. The key to understanding panspermia lies in the study of meteorites, those ancient messengers from space that have crashed onto our planet throughout history. Some meteorites, upon closer inspection, reveal a fascinating secret. They contain organic molecules, the building blocks of life as we know it. The discovery of organic molecules such as amino acids and nucleobases in meteorites lends credence to the idea that the ingredients for life could have originated elsewhere in the cosmos. These molecules, essential for building proteins and DNA, are the very foundation upon which all life on Earth is built. While the presence of organic molecules in meteorites doesn't definitively prove panspermia, it certainly adds weight to the theory. It opens up the possibility that the raw materials for life were delivered to early Earth, potentially jump-starting the process of life's emergence on our planet. The word panspermia might sound like something out of a science fiction novel, but its roots are firmly planted in the ancient world. To understand its meaning, we must travel back in time to the intellectual heart of ancient Greece. The ancient Greeks had a profound impact on the development of Western thought, and their language, rich in nuance and meaning, continues to shape our understanding of the world. Many scientific terms we use today, including panspermia, have their origins in Greek words, demonstrating the enduring legacy of these ancient thinkers. It reminds us that the questions we grapple with today have often been pondered by generations past, their insights woven into the very fabric of our language. Pan, the all-encompassing. Panspermia is a composite word formed from the union of two distinct Greek terms, pan and sperma. Each of these components contributes to the overall meaning of the word, offering clues to the theory it represents. In Greek mythology, Pan was the god of the wild shepherds, flocks, and rustic music. However, beyond its mythological significance, Pan held a deeper meaning in the Greek language. Pan signified all or everything, encompassing the totality of existence. When we encounter Pan in words like panorama, a view encompassing all surroundings, we are reminded of its expansive meaning. Sperma, seeds of life. The second component of panspermia, sperma, takes us to the heart of the theory's central idea, the dissemination of life throughout the cosmos. Seeds in the natural world are remarkable vessels of life. They contain within them the blueprint for an entire organism, dormant yet brimming with potential. Carried by wind, water, or animals, seeds can travel vast distances, taking root in new environments and giving rise to new generations of life. Instead of traditional seeds dispersed across a field, we are presented with the idea of microscopic seeds of life. carried across the vast expanse of space. These microbial travelers, like their terrestrial counterparts, hold the potential to initiate life on other planets, seeding the universe with the possibility of life's emergence. Cosmic billiards. To grasp how panspermia might work, picture the vastness of space as a cosmic billiards table. Instead of billiard balls, we have planets, asteroids, and comets, all engaged in a celestial dance of orbits and collisions. These collisions, while seemingly destructive, are actually crucial for the potential spread of life according to the panspermia theory. Imagine a large asteroid carrying within its rocky crevices the dormant forms of microorganisms hurtling through space. The impact is cataclysmic, sending shockwaves across the planet's surface. Fragments of the planet's crust, imbued with those resilient microorganisms, are launched into space by the sheer force of the impact. They carry with them the potential for life, like seeds scattered by a cosmic wind. The idea of life surviving the violence of a planetary ejection might seem far-fetched, but nature often surprises us with its resilience. Certain types of microorganisms, known as extremophiles, possess an astonishing ability to withstand conditions that would be lethal to most life forms. They can endure extreme temperatures, radiation, pressure, and even the vacuum of space. These hardy microbes become the unwitting passengers on our ejected planetary fragments. Shielded within the rock or ice, they enter a state of dormancy. Their metabolic process is slowed to a crawl. In this suspended animation, they can survive for incredibly long periods, perhaps millions or even billions of years, waiting for a chance encounter with a suitable environment. Yet a fraction of these microbial voyagers endure, their protective shells shielding them from the worst of the cosmic onslaught. As these celestial arcs drift through the vast cosmic ocean, their paths are influenced by the gravitational pull of stars and planets. Their journeys become a game of cosmic pinball, with each gravitational nudge potentially altering their trajectory and bringing them closer to a new home. Our own planet, Earth, with its life-sustaining atmosphere and liquid water, becomes a beacon in the darkness for these wandering fragments. Over billions of years, countless such fragments have rained down on Earth, carrying with them the potential for life from distant worlds. Most burn up in the atmosphere, creating fleeting streaks of light across the night sky. However, some, particularly the larger ones, survive the fiery descent and crash land on Earth's surface. The journey to Earth is just one part of the story. For panspermia to truly be viable, the microorganisms hitching a ride on these celestial fragments need to survive the impact. Can anything, even the hardiest microbe, withstand the forces involved in a planetary collision? The heat generated during atmospheric entry can reach thousands of degrees Celsius, easily enough to incinerate most organic material. The impact itself generates immense shock waves that could obliterate even the toughest microorganisms. Recent studies have shown that certain types of microorganisms, particularly those encased in a protective layer of rock or ice, can survive surprisingly high levels of shock and heat. These findings, while not definitive proof, provide a glimmer of hope for the panspermia theory. Let's imagine for a moment that some of these microbial voyagers do survive the perilous journey and the fiery crash landing. They find themselves on a young Earth, billions of years in the past, a world very different from the one we know today. The atmosphere is thinner, the oceans are warmer, and life as we know it has yet to take hold. The dormant microorganisms, sensing the presence of liquid water and nutrients, begin to stir. Their metabolic processes, dormant for eons, slowly come back online. They begin to divide and multiply, their genetic material replicating, evolving, adapting to this new environment. These microbial pioneers, carrying the genetic legacy of a distant world, become the seeds of life on Earth. Over billions of years, their descendants evolve and complexify, eventually giving rise to the incredible biodiversity we see today. The theory of panspermia, while captivating, wouldn't hold much weight without at least some scientific evidence to back it up. Fortunately, the universe has provided us with some intriguing clues, hidden within the very fabric of celestial objects that have fallen to Earth. These clues come in the form of organic molecules, the fundamental building blocks of life as we know it. Finding these molecules in meteorites, objects originating from outer space, suggests that the ingredients for life might be far more widespread in the universe than previously thought. The presence of organic molecules in meteorites doesn't necessarily prove that life originated elsewhere and was transported to Earth. However, it does lend credence to the idea that the raw materials for life could have been delivered to our planet through these celestial messengers. Skeptics of panspermia often point to the harsh conditions of space as a major hurdle for the theory. The vacuum, extreme temperatures, radiation exposure, and lack of nutrients seem incompatible with our understanding of life's requirements. Enter the extremophiles, a diverse group of microorganisms that defy conventional wisdom by flourishing in conditions that would be lethal to most life forms. These microscopic marvels have been found in scorching hot springs, under crushing pressures in the deep ocean, in the frigid wastelands of Antarctica, and even within the highly acidic runoff of mines. If these organisms can survive such extreme conditions on Earth, it begs the question, could similar life forms, perhaps even more hardy, exist elsewhere in the universe capable of enduring the perils of space travel? In 1969, a fiery streak lit up the sky over Murchison, Australia as a meteorite entered Earth's atmosphere and broke apart, scattering fragments across the countryside. The Murchison meteorite, upon analysis, revealed itself to be a treasure trove of organic molecules. Scientists discovered a staggering array of over 100 amino acids, the building blocks of proteins, within its fragments. Remarkably, many of these amino acids are not found in life on Earth, suggesting an extraterrestrial origin. This discovery fueled the debate surrounding panspermia, lending weight to the idea that life's ingredients might have been delivered to our planet through meteorite impacts. While the discovery of organic molecules in meteorites provides tantalizing clues proving that these molecules, or even microorganisms, could survive the harsh realities of space travel, is an entirely different challenge. To address this, scientists have turned to the power of experimentation, simulating the conditions of space to test the limits of life's endurance. These experiments involve subjecting microorganisms to the vacuum of space, intense UV radiation, extreme temperatures, and even simulated meteorite impacts. Some microorganisms, particularly those capable of forming protective spores, have shown remarkable resilience, surviving these simulated space journeys with surprising tenacity. One such experiment, conducted on the International Space Station, involved exposing spores of the bacterium Bacillus subtilis to the harsh conditions of space for over a year. Remarkably, a significant percentage of the spores survived the ordeal, demonstrating that microorganisms can endure the vacuum, radiation, and temperature extremes of space for extended periods. The search for biosignatures continues with renewed vigor. Scientists focus on identifying specific molecules or patterns. These could include organic molecules, isotopic ratios, or fossilized microbial life. Mars exploration is particularly relevant. Discovering biosignatures would alter our understanding of life's place in the universe. While the idea of microscopic travelers hitching rides on cosmic shuttles is captivating, the sheer hostility of space is a significant hurdle. The vacuum of space poses a serious threat to life. Most organisms would quickly succumb. Radiation further diminishes survival odds. Interstellar journeys can last millions of years. Could any life form truly withstand such a journey? Imagine our microorganisms braving space travel. They've survived the vacuum and radiation. Now they face the cosmic lottery of landing on a habitable planet. Space is vast and habitable planets are rare. The odds are astronomically small. It's like flinging a dart across the universe. The odds are not in favor of our microbial passengers. Even if they find a habitable planet, there's no guarantee of a smooth landing. Entering a planet's atmosphere is chaotic. The intense heat could incinerate our microbial stowaways. The presence of organic molecules in meteorites, often cited as evidence supporting panspermia, is not without its critics. While finding these building blocks of life in objects of extraterrestrial origin is undoubtedly intriguing, it's important to remember that these molecules are not, in themselves, proof of life. They are simply the ingredients, the raw materials from which life can be built. Organic molecules can form through abiotic processes, meaning they can arise without the involvement of living organisms. These molecules have been found in interstellar clouds, the vast reservoirs of gas and dust scattered throughout galaxies, suggesting that they can form in the harsh environment of space. Their presence in meteorites, therefore, might not necessarily point to a biological origin. It's possible that the organic molecules found in meteorites formed through these abiotic processes and were later incorporated into these celestial objects during their formation. In this scenario, these molecules would be evidence of the chemical richness of the universe, not necessarily of life beyond Earth. The panspermia theory, while thought-provoking, faces a significant challenge: the burden of proof. In science, extraordinary claims require extraordinary evidence. While the theory offers a plausible explanation for the origin of life on Earth, it lacks the definitive proof needed to elevate it to a widely accepted scientific truth. Until such proof is found, panspermia remains a topic of debate and speculation. The panspermia theory has profoundly impacted our scientific perspective. It challenges us to expand our view of life beyond Earth, urging us to consider that we are not alone. This shift has ignited a new era of exploration, seeking signs of life beyond Earth. Panspermia suggests life might be more common and widespread than we imagine. The panspermia theory suggests life can arise from inert matter seeded across the cosmos by celestial wanderers. This ignites our curiosity, urging us to explore the universe with renewed purpose. Imagine a universe where every star system holds potential for life, each harboring unique biospheres. The search for extraterrestrial life is a cosmic imperative, a quest to understand our place in the universe. Panspermia, by suggesting that life on Earth might have originated elsewhere, raises profound questions about our own biological heritage. Could we be the descendants of extraterrestrial microbes carrying within our very DNA the echoes of a distant world? This possibility, while still speculative, opens up a universe of possibilities for understanding the interconnectedness of life in the cosmos. If life on Earth did indeed originate from a single common ancestor, as many scientists believe, then panspermia suggests that this ancestor might have arrived on Earth from elsewhere in the universe. This would make all life on Earth, from the smallest bacteria to the largest whales, descendants of extraterrestrial immigrants. This realization has profound implications for our understanding of evolution. It suggests that the diversity of life on Earth might be influenced not just by the pressures of our own planet's environment, but also by the genetic legacy of our extraterrestrial ancestors. Unraveling this cosmic connection could unlock new secrets about the evolution of life on Earth and beyond. The panspermia theory, while still a subject of debate and speculation, has undoubtedly enriched our understanding of the universe and our place within it. It has expanded our view of life, ignited our sense of wonder, and spurred us to explore the cosmos with renewed vigor. The search for extraterrestrial life, fueled in part by the intriguing possibility of panspermia, continues to captivate our imagination and drive scientific discovery. As we continue to explore the cosmos, developing new technologies and sending probes to distant worlds, we will undoubtedly uncover more clues about the origins of life and the possibility of life beyond Earth. Whether panspermia proves to be the definitive answer or not, its legacy will live on, inspiring future generations to ponder the mysteries of life and our place in the grand tapestry of the universe. The journey to understand our cosmic origins is far from over. It has just begun.